Pre-calc honors. All right, let's start 9.3. The complex plane and De Moivre's theorem. First definition is this here, complex plane, but can you also add an complex number? Okay. All right. So the definition is a complex number such as z equals x plus yi, or if you see z equals a plus bi, they're exactly the same, okay? Where, remember in algebra 2, I is the square root of -1, and x and y, or if we use, or, and how about this, or if we use a and b, or a and b, okay, are real numbers. So let's kind of graph it out a little bit. So in the complex plane, remember we have the Cartesian plane, aka rectangular, then we have the polar grid. Now this is a complex plane. So we have real numbers axis over here. Okay, then over here, up here on the y-axis, we have the imaginary number axis. Okay, so we have real axis and imaginary. So i.e., let's make up something really quickly. We have 5 minus 3i. So how would we graph that? This is just a dot. Okay, so this is a dot. So we're going to go 5 unit, that's a real number. So think of it as a plus bi, or think of it as x plus yi. Okay, so we have 5, 1, 2, 3, 4, 5. That's 5 real numbers, right? 5 to the x-axis, so that's positive, goes right. Then we have 1, 2, 3, so -3. So here we go. So this right here is 5 minus 3i, so that's your dot. Now whenever you see this, z equals -2 minus 4i, or z equals positive 10 plus 100i, it doesn't really matter. So if you see this, it is something like this. So we are still going on the real axis a -2, then we'll go down 4, so we'll do this one. So this is your z. So this is your z, okay? Just like that. So that's your z. Or you can write z equals -2 minus 4i, just like that. Or you can just use a z. Now, as you know already, back in whenever you first start learning absolute value. So an absolute value would denote the distance. So this right here, an absolute value of z, would denote the distance of that equation, okay? Magnitude or modulus. Should have just had the columns over there. So let z equals x plus yi be a complex number. The magnitude or modulus of z denoted by an absolute value of z. Okay, so now the magnitude is the absolute value of z, is defined as the distance from the origin to the point x comma y. So the absolute value of z, if we were to look for the distance, we would use the distance formula, right? And the distance formula would be the square root of x2 minus x1. But what if x2 is just x, and x1 is the origin, and we square that, then add y2 minus y1. Well, y2 is just y, y1 is at the origin, so we can just say something like this. Now, to simplify this further, would you agree then the absolute value of z, which is the distance, is simply the square root of x squared plus y squared, if we have the point from the origin? Well, have we not seen this formula somewhere? The square root of x squared plus y squared. Isn't this the same as the radius formula if you were given an ordered pair in rectangular form and you were trying to find the radius? I know, right? They're totally related. All of these are related to each other. The absolute value of z. So as you can see here, this is another way to say the magnitude. So absolute value of z is the magnitude. Okay, and as you know, we use this to represent the magnitude. Since since z equals x plus yi, then the conjugate okay. So in your book, we use the z with the bar on the top to represent the conjugate, and the conjugate is when we change the sign right in the middle, just like that. So the conjugate equals x minus yi. So what if we multiply the conjugate pair together? So that means we want to multiply z to z bar, which leads us to an equation x plus yi times x minus yi, which equals to x squared. Technically, this is minus y squared I squared, but I squared is -1. So this is really x squared plus y squared. Well, that equals to z times z conjugate, but if we are thinking about, okay, so this equals to z times z conjugate, so think of this equation for me. Well, but would you agree if we're looking for the distance of z, okay, if this is the distance of z, would you agree then, I'm going to go one step further, z and z conjugate will have the same exact distance. So if we are talking about distance, they are identical. So technically we can write z squared, which equals to x squared plus y squared. But what if we want to take the square root? Well, would you agree then that the square root gives us back to z equals the square root of x squared y squared? Now, this is just one more way to look at how we come up with the formula for the distance, aka, think about it, the magnitude, aka it's the same formula for the radius, okay? Next definition says polar form. So if the radius is bigger than or equal to 0 class, and theta is in between 0 and 2 pi, inclusive at 0. The complex number z equals x plus yi is z equals, as you know already, x in polar form is radius times cosine of theta, and y in polar form is radius times sine of theta, and then we stick an I, imaginary number, at the end. But we can make this prettier by factoring out the radius. So z equals radius cosine of theta plus, and then we stick an I in the front here, I sine of theta. So I do want to highlight that formula. Okay, so highlight this formula. This right here, guys, is the polar form of complex number. And again, be mindful of those restrictions, okay? So theta has to be a positive first revolution and radius got to be negative. Okay, so we got some theorems going on here. Let z1 equals radius sub 1 times cosine of theta sub 1 plus I times sine of theta sub 1. That is the polar form of complex number. And z sub 2 equals r sub 2 times cosine of theta sub 2 plus I sine theta sub 2. Be two complex numbers. Then, when we multiply the two complex numbers, all we're doing is really adding the angles together and then multiply the radii together. Now, if z sub 2 is not going to equal to 0, because when you divide, you can't have a denominator equal to 0, then we can divide them. Well, dividing them is very similar. Then we divide the radii and then subtract the angles, which you do need to know these formulas, okay? Last definition, De Moivre's theorem. If z equals radius times cosine of theta plus I sine of theta, this is just the polar equation for complex, is a complex number, then z to the nth power equals r to the nth power times cosine n times theta, close that up, plus I times sine of n times theta. Now, this makes a lot of sense because when we were multiplying just two z's, what did we multiply? Three z's, right? Then would you agree, especially if the z's are identical, so if we multiply three z's, then we would just take three radii and multiply them, and we would add up all the angles. But if the z's are identical, then we're just going to raise them to the power of n. Now, what is n? N can be any integers, that means whole numbers, so 1, 2, 3, 4, 5, okay? And n has to be bigger than or equal to 1. Example 1. Plot each complex in the complex plane and write it in polar form. Express the arguments in degrees. So this one, they do not want us to use radians, okay? So complex polar form, remember the restriction. Radius is got to be, do you guys remember what the restriction for radius for complex form? Has to be bigger than or equal to 0. And since we are in degrees, theta has to be at least 0 degrees and all the way to 360. So that has to, we have to follow that restriction if we are writing in polar form. All right, first things first, let's write down the formula. Okay. Oh, let's plot first. Duh. Okay, so plot, let's call it A. Okay. A, we are going to plot. Make sure we write real number axis here, and this is the imaginary axis. Axis, I meant. Radical 3 is in between 1 and 2, and we have 1 I. So just like that. So that's it. Okay. Now we will make a line here because that's a z equals. Now guys, if you just have a dot, I'm okay with that too. No worries, okay? Then over here, let's go and do part A over here as well. Let's graph both of them at the same time. I now have, let's see, we will have, I need 9 times rad 3. Okay, that's a lot of positive x-axis, and I need negative 9y. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is your imaginary axis, and this is our real axis. Okay, so technically this is a dot, but again, it's not really important that if you give me a dot or not a dot. Okay, I'm not really strict on if you give me a dot or a segment. No big deal. So 9 rad 3, let's see. I'm probably going to rescale my x-axis. So I'm going to rescale it, guys, by 2, 4, 6, 8, 10, 12, 14. I'm going to extend it a little bit longer. 14 and 16. The reason I'm rescaling it is because 9 rad 3 is about in between 15 and 16. So I need this much like that. Okay, I'm not going to rescale the y because I did make 9 tick marks. So this is really technically your dot of 9 radical 3 take away 9i. Now in your book, it may connect this to the origin. That's okay too. Okay, so you can connect it or you don't have to. It's not a big deal. As long as you have a dot, then I'm good. If you have a dot and a segment, cool. If you just have a dot, also okay. Then part B says, now write it in polar form. So let's go and do part B. How about if I use a different color for part B? Cool, okay. So part B, we would have the polar form z equals radius cosine of your angle plus I sine of your angle. Radius got to be positive, so let's find the radius. Radius is the distance of z, which is the magnitude of z, which is the formula of x squared plus y squared. Okay, x is going to be radical 3. So radical 3 squared is 3. Y is up 1, so that's just going to give us 1 in there. That's going to be square root of 4, will give us a radius of 2, and that's definitely positive, so we are okay with the restriction of radius. Then we need to find theta. Theta is formula sets tangent inverse of y divided by x. Now remember, if it's in quad 2 and quad 3, then we have to go and add pi, or in this case 180. But because it's in quad 1, we don't have to worry about it. So tangent inverse of, again, your y value is 1, so 1 divided by rad 3, which is an angle that we do know perfectly. This is 30 degrees. Well, check, right? Positive angle, positive radius. We're going to use those to put our z equation together. So z equals radius is 2. Cosine of 30 degrees plus I sine of 30 degrees, and box that up. Not too bad, right? Okay, let's do this again and over here. If you don't have enough space, try to squeeze that in. Similarly, the polar form is z equals radius times cosine of theta plus I times sine of theta, and we have to follow the restriction of radius and theta. They both have to be positive. So radius is the magnitude of z, which is going to be the square root of x squared plus y squared, which is x happened to be 9 radical 3, and I square that, so that's going to be 81 times 3. Then plus, okay, y is negative 9, and I want to square that, so that's going to be 81 times 3, and then plus 81. So under the radical, I have 324. So that's right now. I'm going to leave that right there. I don't want to do anything yet. Actually, let's go up. Let's simplify, because that's a perfect number. I just want to make my square root a little bit. That's 18. All right, so let's leave. Now we can leave 18. Then let's find theta equals tangent inverse of y divided by x. We are in quad 4, so if we are using the calculator, it will give us a negative degree, but the restriction for polar said we have to be positive, so make sure you guys add a full revolution, okay? So tangent inverse of y value is negative 9, x is 9 rad 3. Let's reduce that. That means theta equals tangent inverse of 1 over negative rad 3, which will give us a negative 30 degrees. And you can test that out using your calculator. But remember, restriction sets, we cannot have a negative angle for polar form. So we will now go and add, because from here to here is negative 30 degrees. So what we're trying to do is go this way, okay? So we can add 360 degrees, or you can take 360 minus 30, which is exactly the same thing. That will give us 330 degrees. So now we have enough to write. So that's going to be 18 cosine of 330 degrees plus I sine 330 degrees. Box that up. And again, in polar form, radius and degree must be positive. Okay, y'all?